Chapter 7, Diagonalization and Quadratic Forms. Section 7.1, Orthogonal Matrices. A square matrix A is said to be orthogonal if its transpose is the same as its inverse, that is, if A inverse is equal to A transpose, or equivalently, if A times A transpose is equal to A transpose A, which is equal to the identity. So if A transpose cancels out A. So as an example, how about we determine whether the given matrix is orthogonal? So let's compute A transpose A. So that means that we're taking, let's see, A transpose would be if we take this entire row and make it the first column. So we get 3/7, 2/7, 6/7, and then minus 6/7, 3/7, 2/7, and then 2/7, 6/7, and minus 3/7. So then we'll multiply that by A, which I'll just repeat as 3/7, minus 6/7, 2/7, 2/7, 3/7, 6/7, 6/7, 2/7, minus 3/7. And at this point, you can do the multiplication by hand or just plug it into a calculator, and you'll see that, yes, you in fact do get the identity. So these matrices, this matrix is orthogonal because it does, its transpose is its inverse. Recall from Table 5 of Section 1.8 that the standard matrix for the counterclockwise rotation of R2 through an angle theta is A equals this matrix right over here, cosine minus sine, sine cosine. Let's verify that this matrix is orthogonal, along with the reflection matrices in Tables 1 and 2 of Section 1.8. Okay, so let's take A transpose A to start. So that's going to be equal to cosine minus sine for column 1, and then sine cosine for column 2. Multiply that by cosine minus sine, sine cosine, and we in fact do get the identity because of the sine squared cosine squared equals 1 business. Everything will end up canceling. So if I also look at the reflection matrices, let's see where we have the matrix that takes xy and sends it to x minus y. So then we need to look at 1, 0, 0, minus 1 and its transpose. Notice that the transpose is the same thing in this case. So we'll multiply those together, and we do in fact get the identity. Okay, so that matrix is orthogonal. Okay, how about the one that takes xy and sends it to minus xy? Pretty similar to the last one. So that'd be minus 1, 0, 0, 1. And when we transpose it, it also stays the same. Multiplying together, again, we get the identity. So that matrix is orthogonal. Let's now check the one that swaps x and y. So t of xy equals yx. That'll be 0, 1, 1, 0. When we transpose that, it stays 0, 1, 1, 0. And multiplying that also gives us the identity. Okay, how about those three-dimensional ones? Let's look at the matrix that took x, y, z and made it x, y, minus z. So it shouldn't be too surprising that, again, transposing these matrices doesn't change them. But I'll write it out anyway. So 1, 0, 0, 0, 1, 0, 0, 0, minus 1, and then multiply that by the original one, which is the same in this case, 1, 0, 0, 0, 1, 0, 0, 0, minus 1. Okay, so we get 1, 0, 0, 0, 1, 0, 0, 0, 1 for our density in R3. Let's look at the matrix that similarly sent x, y, z to x minus y, z. Okay, so that takes 1, 0, 0, and then we have a minus 1 for the y. Okay, multiply that by well, this was the transpose, but the other one's going to be the same anyway. And again, we get the identity. Okay, one more to check. We need t of x, y, z equal to minus x, y, z. So we have a minus 1 for the x, and then the rest is the same. And transposing doesn't give us any change. And multiplying, we get the identity again. Okay, next up we have this theorem that the following are equivalent for an n by n matrix A. That A is orthogonal is equivalent to the row vectors of A forming an orthonormal set in Rn with the Euclidean inner product, which is in turn equivalent to the column vectors of A forming an orthonormal set in Rn with the Euclidean inner product. So the row vectors form an orthonormal set, the column vectors form an orthonormal set is the same thing as A being orthogonal. So that's one of the reasons why we might care if A is orthogonal or not. Our next theorem says that the transpose of an orthogonal matrix is orthogonal. The inverse of an orthogonal matrix is orthogonal. A product of orthogonal matrices is orthogonal. And if A is orthogonal, then the determinant of A has to either be 1 or minus 1. So let's do an example where we verify the theorem that we just did, the part D of it, for the matrix given. Obviously, we're not proving the theory in entire generality by just doing this as one example, but we'll just check that it works for this one. Okay, so notice that in this case, if I look at A, the transpose of A multiplied by A, and it would end up with a ton of cancellation, we'd end up with the identity. So A is orthogonal. So let's check the determinant. So the determinant of 1 over square root of 2 minus 1 over square root of 2, 1 over square root of 2, 1 over square root of 2 is equal to half minus a half, which in fact is equal to 1. If you were to swap the rows, so if I was to write minus 1 over rad 2, 1 over rad 2, 1 over rad 2, 1 over rad 2, I just interchange the first and second rows, and I take the determinant, I would get minus a half, so it would be minus 1. And notice this matrix is also orthogonal. Another way you can see that it's consistent with the previous theorems is that if you look at the rows, these two rows written as row vectors, they're an orthonormal set in R2. So the matrix has to be orthogonal using the previous theorem. So swapping the rows means that there's still an orthonormal set. Doesn't matter which row comes first, so the matrix will still be orthogonal. And notice the determinant just changes to -1. If A is an n by n matrix, then the following are equivalent. A is orthogonal. The length of AX is equal to the length of X for all X in Rn. AX dotted with AY is equal to X dotted with Y for all X and Y in Rn. Let's prove that A implies B. So if A is true, so we're assuming that A is orthogonal, so we have A transpose A is equal to identity. So then let's look at what the norm of AX is, the length of AX. So that's AX dotted with AX. Take the square root of it. Okay, so then I can move over the A, since AU dotted with V is the same thing as U dotted with A transpose V. We saw that in section 3.2. You can move over the matrix as long as you take the transpose of it. So we do that over here. We move over A and it becomes A transpose. But remember, we have A transpose A equal to the identity. So this is just the identity, so it cancels. We just have X dot X. And X dot X to the half power, the square root of that is literally just the length of X. So that shows that if A is orthogonal, we have B. So now let's show that B implies C. So we'll assume that the length of AX is equal to X for all X in Rn. Then let's look at what happens when we take AX dotted with AY. We want to show that it's X dot Y. Okay, well, we can use our formula also from 3.2 in order to rewrite our dot product in terms of lengths. And then we can just take the A and factor it out and do that for both. But then remember that AX is equal to the length of X for all X, so that includes the vector X plus Y and X minus Y. So that means it just must be the length of X plus Y and X minus Y. And then rewriting the formula again back to the dot product, we get the result we want. Alright, now let's show that C implies A, so they all imply each other. So we'll assume that we have that formula, AX dot AY is equal to X dot Y for all X and Y in Rn. So that means that we can throw in A transpose A into there, right? Because I'll just take A from our assumption, move it over again, becomes A transpose, and just change the order over here so that the X dot Y is on the left. Then I'll subtract X dot Y from both sides and factor out the X so that I get X times this thing is equal to 0, which is the same thing as then factoring out Y and saying that X dotted with this thing times Y is 0, but it holds for all X in Rn. So that holds in particular if X is equal to A transpose A minus I dot Y. So that's the same thing as just rewriting this and plugging in, instead of X, plugging in A transpose A minus I Y. So it's the same thing as the dot product of these two guys being 0, which shows that A transpose A minus I Y must be equal to 0. But that must be satisfied for every vector Y, so I can just plug in some non-zero vector in for Y and see that this thing would have to be the 0 vector in order for it to work for every Y. So that means that this thing is equal to 0, move this to the other side, and you get A transpose A is the identity, which means A is orthogonal, exactly like we wanted to prove. Let's do another theorem. If S is an orthonormal basis for an n-dimensional inner product space, V, and if US and VS are given as these coordinate vectors, then we have that the length of U is the square root of all of the U1 squared through UN squared. The distance between U and V is the square root of the differences between them. The inner product, U and V, is just the dot product. It should kind of make sense because we have these coordinate vectors, so it makes sense that they would behave like Euclidean space, even though they behave like, you know, Rn, even though it's just an n-dimensional inner product space, even though it's more general. Let V be a finite dimensional inner product space if P is the transition matrix from one orthogonal basis V for V to another orthogonal basis for V, then P is an orthogonal matrix. Okay, let's do an example. How about we look at the x prime, y prime coordinate system. Let's let that system be the system obtained by rotating a rectangular coordinate system, xy coordinate system, counterclockwise about the origin through an angle theta. Let's write the coordinates x prime, y prime in terms of the coordinates xy. So to start, let's let u1 and u2 be unit vectors along the positive x and y axes. So these are in regular xy space, our kind of original xy coordinate system, and let's let u1 prime and u2 prime be unit vectors along the positive x prime and y prime axes. Let's see what happens, or let's see what we have to do to u1 and u2 to turn them into u1 prime and u2 prime. So we're going to look from basis B equal to u1, u2, and we'll see what happens, or see what we need to do to make it into B prime equal to u1 prime, u2 prime. So we're taking, well, our basic equation is going to be that the coordinates x prime, y prime are equal to some transition matrix P times xy. So that transition matrix P we can write as u1 rewritten in terms of B prime adjoined with u2 in terms of B prime. So let's see what those vectors are. Well, how about we make a little picture. So let's say, well, this is going to be, I'll make this x prime and y prime. So here's x prime, here's y prime. So this is after it was rotated by some angle theta, or after x and y were. So about x, like I say, was originally over here. So here's x, and then here's y perpendicular. Okay, so we rotated some angle theta, right? That's how we got from over there to over there. And we have u1 is the vector over here, right there, along the x-axis, and then u2 is the unit vector along the y-axis. And I know that it makes, well, for u1, how about I do that first? It makes some x direction cosine theta if the angle is theta. In the y, it's going below, so it'll be minus sine theta. And then similarly for u2, it's going to be cosine theta. You have to be a little bit careful over here because remember this is the y So it's kind of hard to see, but it rotates through, and so it switches, even though usually you would see this as sine. So then over here, this is sine theta. Yep, because remember, this is the y-axis, so you kind of have to rotate yourself and see that this is cosine and this is going to be sine. Okay, so now I can write u1 in terms of b prime as cosine theta minus sine theta. And I can write u2 b prime as sine theta cosine theta. So that means that I have x prime y prime equal to p times xy, so that matrix P will be cosine theta minus sine theta for u1 b prime, and then sine theta cosine theta for u2 b prime times xy. But notice that's basically the rotation equations. It's where we just have x prime equal to x times cosine theta plus y times sine theta, and y prime equal to minus x sine theta plus y cosine theta. Okay, so that's one way to see that these are our rotation equations for R2. Okay, let's use those rotation equations to find the new coordinates of the point 2, 1 if the coordinate axes of a rectangular coordinate system are rotated through an angle of pi over 4. So let's look at what the sine of pi over 4 is first. Well, notice that's the same as the cosine of pi over 4. They're both the same at 45. And they're rad 2 over 2, or 1 over rad 2, however you like to think about it. So then I'll have x prime, y prime equal to 1 over rad 2 minus 1 over rad 2, 1 over rad 2, 1 over rad 2 times xy. Looks a little familiar. And I'll have x prime, y prime equal to, in this case, 1 over rad 2 minus 1 over rad 2, 1 over rad 2, 1 over rad 2 times the point they want us to look at, 2 minus 1. Just replacing that for xy now that I have my formula. Okay, so multiplying, we get 1 over rad 2 minus 3 over rad 2. So that's what the new point x prime, y prime is after the rotation. It's 1 over rad 2 minus 3 over rad 2. Let's do it in 3 dimensions now. How about we let the x prime, y prime, z prime coordinate system be the system obtained by rotating a rectangular xyz coordinate system around its z-axis counterclockwise through an angle theta. Let's write the coordinates x prime, y prime, z prime in terms of the coordinates x, y, z. So we're going to take a basis B built of unit vectors, same as we did last time, where we have u1, u2, and u3, and that'll become b prime equal to u1 prime, u2 prime, u3 prime. And let's draw what's going on here. It's just going to rotate around the z-axis. The z-axis won't change. So z will be z prime, but x and y will change. Those will rotate a little bit. So I'll make this x, y, z. Z will stay z prime because it's just rotating around over here. So there's no difference there. However, the rotations will affect the x and y axis. X could move, let's say, over here by an angle theta. So this will be our x prime. And similarly for y, it'll move, let's say, over here. That'll be y prime. So let's see if I can put on, here's u1. And then on y, I need u2. And then on z, I need u3. Notice u3 will be equal to u3 prime because z is equal to z prime. So we just need u1 prime and u2 prime on the y prime. Okay, that's a good picture, or good enough at least. So now I can use that to write the u1 prime in terms of b, if I want to go from b prime to b, because at least in the picture I drew, it's a little bit more clear how we're going from u1 to u1 prime. It doesn't really matter how you draw your picture as long as you're a little bit consistent when you're doing your deductions. So if I'm going from u1 to u1 prime in my picture, then that means that I should have cosine for x, sine for y, and then the z will just be 0, not changing z at all. And for u2 prime, in terms of b, it might take a little bit of convincing, take a look at the picture carefully, but it's minus sine theta cosine theta 0. And then u3 in terms of b is easy because it doesn't change. The unit vector along the z-axis will just be 0, 0, 1. Okay, so now with these three vectors rewritten, I can come up with the transition matrix from b prime to b. So that would be p equals cosine theta sine theta 0 minus sine theta cosine theta 0, 0, 0, 1. And I can just take p inverse in order to get from b to b prime, which is what I want. So p inverse will be equal to cosine theta minus sine theta 0 sine theta cosine theta 0, 0, 0, 1. So I'll take the p inverse in this case, and I'll use that to come up with a formula for x prime, y prime, z prime. So that'll be equal to cosine theta minus sine theta 0 sine theta cosine theta 0, 0, 0, 1 times any point x, y, z.